In this segment, we will introduce instantaneous rate of change, which is a generalization of the average rate of change. We will start from taking a look at the definition 1 given over here of the average rate of change. We notice that the average rate of change is assigned to the entire interval. That is, the value that we compute in the fraction over here, it is not associated with point A or point B. In fact, this value is associated with any point on the interval. So that value sort of spreads out from the beginning of the interval to the end of the interval and is the same for the entire interval. This may sound not very satisfactorily because we suspect that this rate may fluctuate with time, and we may well benefit from looking at average rates over shorter intervals of time so that we have information about more precise location in time. Unfortunately, the table on the left does not provide us enough data to look at a shorter intervals in time. So what we could do, we could feed that data into a function, and then we can try to answer the questions about rate of change on a shorter intervals. So as a matter of fact, it's not very difficult to feed that data. I'm just giving you the answer here. That function feeds the data points pretty well, as you can see. How do you find a function that fits it? Well, as a matter of fact, you can use calculus creatively to realize that this data on that table is coming from an exponential function, and then you can use differential equations and a little bit of calculus to write down that formula more. So it's not guessing it out, but rather obtaining it through a rigorous process. So nevertheless, for the sake of this lesson, we will just accept that function as a good approximation of the data, and we will use this function to answer questions about average rate of change. So here we go. We will use this fitted function to fill out the following table. We will zoom on the value of t equals 12, and we will consider interval that is getting smaller and smaller and smaller. We'll pick a value h. Well, in particular, we'll start with 0.1, then we go 0.05, 0.2, 0.5. As you can see, the value of h is halved as we go from one cell to another cell. And we will evaluate average rate of change on the interval from 12 to 12 plus h. So these intervals will get shorter and shorter and shorter. So to do this computation, I will go back to my favorite tool, the Google Sheets over here, and I have a table prepared here with the values of h. The value of t, where we would like to evaluate the average rate of change, is 12 over here, and I would like to use the sheets to compute that table. I'll have to make several steps, and once again, Google Sheets is probably not the most convenient way to use it. However, it's very accessible, so I will do it in Google Sheets, but you can do it in your software, your favorite software of your choice. It could be Dismas, it could be MATLAB, it could be different, it could be Mathematica. So all of these are quite good to use with this problem. So how do we program the sheets? Well, we can put some simple formulas. So in particular, we can take, let's program the value of t plus h. So t is 12, and I will put here $8. So when I drag that formula, it does not disturb the value of that cell. And then I will take the value of t over here, and I will add the value of h. Right. So as you can see, t plus h is 12.1. If I drag this formula down, I will automatically, the formula will automatically adjust, and I will have values of t plus h. Now it's time to write down value of the function. So value of the function is given here as, right here, as this exponential function. I would like to code that function in this cell. So on the first I'll have this 60.0, that's a coefficient, multiplied by, then I'll have a parenthesis 1 minus, exponential function is coded as exp, and here I will have that coefficient negative 0.069 times the value of the variable, and I will put this value of t b2 over here, and I need to have a couple of closing parentheses. Ta-da! We have the value of the function at t equals 12. Now, if I now take that function, well, I can technically drag it, but I probably don't want to drag it. I'll just copy, and I will paste it into this cell. Let's see. I need to adjust it. Instead of b2, I would like to use a different cell, this cell, b5. So now, that's the same function evaluated at t plus h. Now I can drag it, and these are going to be the values computed at all of those values of t plus h listed. Now, I will use the column to compute the average rate of change. So we need to take value of the function at t plus h. Okay, so let's write it down. What exactly we're trying to compute? We're trying to compute value of the function at 12 plus h minus value of the function at 12 divided by h. So, well, this table allows us to tap on every value in question, so here we go. So first, the difference. We need to take that, and we need to subtract value at 12, which is this guy. Now, as I will be dragging, I don't want that cell that is shown in purple to change. So I will put a dollar in front of 2, so it will be immune to dragging now. And the value of h that corresponds to that value is over here. So here I go. So I will now drag it, and I have all of these values computed very quickly. So let's take a copy over here and paste it. All right, I'll have to paste it, and I have to paste it right into this array. Yeah, here we go. All of the values are pasted. Take a closer look at these values. Maybe we will notice something interesting. Now let's take a look at the numbers that we computed for the average rate of change. As the parameter h is getting smaller and the interval on which we compute the average rate of change getting smaller, the numbers that we compute begin to look like each other. In particular, if you look at this last number, the number before it, and the number before it, you will see that these numbers have the same 4 digits, 1808. Now, all of the numbers that we computed have the same 3 digits, 1, 8, and 0. So what we observe the process of convergence. So if we continue the process of reducing h indefinitely, then we will be computing an infinite sequence of rates of change corresponding to smaller and smaller and smaller intervals. If these numbers that we obtain are converging, then what happens is that in that case, the instantaneous rate of change is defined. Specifically, let's take a look at the definition too. Suppose we have a function that is defined on an interval, and we pick a point at the interval, point x, then we say that the instantaneous rate of change of function f at point x is given by the following formula. And we have limit as h approaching 0 of the following fraction. In the numerator we have f evaluated at x plus h minus f of x, and in the denominator we have h. So it's a change in the function divided on the change of the variable. If this limit exists, then we say that the instantaneous rate of change is defined at a point. So we will continue looking at some examples of evaluating instantaneous rate of change using this definition in the next segment.